So if we consider code 1 with the received sequence of 110011, then essentially there are two possibilities. Either that sequence would have been decoded as x3, x1, x1, x3, like how we just described, or it could have been decoded as x3, x2, x3. So code 1 is posing some ambiguity. In other words, it's not uniquely decodable. There are a couple of possibilities there. Now let's take code 2. We assume a student in the class have come with a different coding, code 2. In the code 2, the idea is the given discrete memoryless source x1, x2, x3 will be coded because the probability of x1 is higher. We will code it as 1. The probability of x2 is 0.2. So it occurs less frequently. So we give more code word length. So it's 0, 0 and 0, 1. Now, if we take the same received sequence, 1, 1, 0, 0, 1, 1, and when we try to decode with the coding 2, so many receivers and in decoding application, the system has to be aware of what was the coding scheme that was used. Okay, that's fairly important here. So if the receiver knows that code 2 was used, then it will try to decode in a way. It's like this. Okay, the first is 1. So 1 would be decoded as there's one possibility. So it would be x1. The next one would be another x1. Then you have 0, 0, which is x2, x1, and x1. Okay, so the given received sequence 1, 1, 0, 0, 1, 1 will be uniquely decoded in this case as x1, x1, x2, x1, x1. Okay, using code 2. Okay, using code 2. So there you go. So we have two coding schemes. You could have other coding schemes as well. Two coding schemes which has followed our intuition and the theory that most probable events will be given lesser bits and vice versa. By using that intuitive feeling, we have designed two codes, code 1 and code 2, but it happens that code 2 is uniquely decodable. Okay, now why that's possible? So the idea that we are getting here is that if you could see, code 2 is uniquely and instantaneously decodable. So therefore, for code words to be uniquely and instantaneously decodable, one of the main condition is that no code word should be a prefix of another code word. Okay, no code word should be a prefix of another code word. So if you consider code 1 as an example, code 1, if you see for x1, which is coded as 0, it's a prefix in x2. Okay, it's a prefix in x2. In other words, 0 is a prefix in x2. It's 0, 0. So if you take code 2, none of the code word like x1 is not a prefix of x2 or x3, and the same is true with x2 and x3 as well. So none of the code word is a prefix of another code word. So that's an important condition if you want it to be uniquely and also instantaneously decodable. So that's why code 2 is preferred because it's what we call a prefix-free code word. Prefix-free code word. Okay. So this prefix-free coding allows us to design schemes, encoding schemes, which are pretty unique and there is no ambiguous at the receiver. Okay, so that's a thing to consider here. It's known in general, the prefix-free codes follow something called a Craft inequality here. What it says is that if you take the average length of the code word, so if you consider this example of code 2, the average length of code 2 is basically probability times the length of the code. So x1 has a length of 1 bit and the probability was 0.7. So it's 1 times 0.7, whereas x2, the length was 2 bits and in terms of the probability is 0.2. X3, the length was again 2 bits and the probability was 0.1. So this is average code word length. So the average code word length is not just the regular average or the mean, it's more like a probabilistic or statistical mean. So here it turns out that the average here is 0.7 plus 0.4 plus 0.2, which turns out to be 1.3. Okay, so 1.3 bits per symbol or sample, okay, is the average code word length for code 2, and it's also same with code 1, because code 1 is also having the same average code word length. So this is your L value that we are looking at. So the average code word length L follows in prefix-free coding. It follows something called Craft inequality, which is given like that, where the average code word length is bounded between entropy and entropy plus 1. Okay, you could also compute the entropy of this given source, which is simply by using the log of the probabilities and adding them, okay, to the base 2, like what we have seen before. When we do this, you will find out that the average code word length lies between these two extremes, which is entropy and entropy plus 1. So the key message here is that we have to follow a coding scheme which is prefix-free. Okay? Prefix-free. And that allows us to build systems which could be implemented without any confusion in a coding scheme for lossless transmission of biomedical signal information. Okay, this is even more important in this current virtual care in the COVID pandemic context, because a lot of the things are telemedicine, teleconsultation. So the transmission of the physiological signals along with other medical and health records is all done over internet or through communication channels, and conserving the bit or making sure that information is compact is so essential to preserve the bandwidth. Okay, so that's why the compression is important, and we do have formal information theory to provide this prefix-free coding. Code 1 and code 2 we just designed through our intuition, because it was a very simple 3 sample case or 3 symbol case, x1, x2, x3. We knew the probability and we went ahead with this. Is there a formal way to design it? Yes, obviously there's a very popular scheme of designing the prefix free code, and one such example is called the Huffman code. So Huffman coding is one of the major ideas behind lossless compression of information. And it really is so applicable in medical context, because in medical domain, we don't really expect a lossy compression. Lossy compression might be okay in application where you deal with, for example, audio files and video files, because mathematically they're lossy in those video and audio. But from the point of perception, they appear to be lossless. Okay, good example is in audio we have MP3. Yes, it is mathematically lossy, but for our ears, MP3 it doesn't cause much distortion. In other words, it appears to be lossless. Same thing in images, as we know, we have the format called JPEG. It's a lossy compression scheme. But here, what we are talking is a lossless compression scheme. To give an example, our zip commands in basically packing the files, WinZip, those things use a lossless compression, and it's obvious in lossless compression we don't get much of a compression efficiency because we want to mathematically preserve all the information. Okay, so Huffman code is one such way to proceed with a prefix-free coding scheme, and Huffman coding is very simple. Okay, it basically involves 3 steps. I would say the first step is that you get the probability distribution function of your symbol. So let's assume your biomedical signal has 4 levels. It takes 4 levels, x1 to x4, and each one occurs with the different probabilities. So you arrange the probabilities first in descending order. Okay, so that's the step 1. So here you could see 0.4, 0.35, 0.2, 0.05. So you arrange them in descending order. Then you start from the bottom. You basically take the two lowest probabilities and you combine them. So here, the very first example is that we have taken x3 and x4, which has a probability of 0.2 and 0.05, and we have basically combined them to get a new probability, which is 0.25, okay? Because 0.2 plus 0.05 is 0.25. Now, in the next step, you do the sorting again. You again sort these probabilities in descending order. So when we see, we have three probabilities now, 0.4, 0.35, and 0.25. So again, they're arranged in descending order, 0.4, 0.35, and 0.25. Going back to the same process, we combine the two lowest probabilities. In this case, it happens to be the two lowest are these two branches, 0.35 and 0.25. We combine them and it has become 0.6 now. That's a new probability. Okay. So that's the second iteration. Now in the third iteration, you're left only with two sources now, one with a probability of 0.4 and the other one is 0.6. Again, you arrange them in descending order. So what happens is the 0.6 goes above now because we are arranging descending order, and 0.4 comes to the bottom. Okay, so we combine these two things and we get the new probability, which is 1. That's the final step, because when we add all the probabilities, it should add up to 1. So that's the final step. So in 3 steps, we have designed an encoding scheme using the Huffman process. Now, how do we give the codes? Once we finish this Huffman tree structure, once we got the final probability to be 1, now we can go with the standardization. We use the upper branch code as 0 and the lower branch code as 1. So here, this one is 0, this one is 1, upper branch is 0, this is 1, 0, 1. Okay, so you could also go 1, 0 at the top, 1 at the top, 0 at the bottom, 1 at the top, 0 at the bottom, but you have to be consistent, you know, in whichever way you proceed. So here we decided to go the upper branch to be 0 and the lower branch to be 1. When we do this thing, now we read the code words in a backward direction. So the code word for x1 we will start from here. So this is the code word for x1, which is 1. And if you see the code word for x2, x2 branches, what are the branches that connect x2 is this branch 0, 0. So that's the code word for x2. Similarly, for the branch for x3, x3 is connected to this branch again, 0. So x3 is this branch 0, 1, 0. Okay, 0, 1, 0. So we got to read it backwards. Likewise, let me take another color to just to differentiate. For x4, the connecting branches, this is a branch that connects x4. So the green one is the thing that connects x4. So the code corresponding to x4 would be 0, 1, 1. Okay, 0, 1, 1. Okay, so here we go. Now the given 4 samples or symbols are encoded. Okay, similar to what we did before, we derived those codes in a more ad hoc manner. Now we have done more systematically by using Huffman coding, by simply using the probability information and tying the two lower probabilities, then again sorting them in descending order and proceeding to the process until we reach 1. By doing this, x1 is now been coded as 1, x2 as 0, 0, x3 as 0, 1, 0, and x4 as 0, 1, 1. Okay, so this particular configuration is prefix-free. Obviously, none of the code is a prefix to another code word, and this process is the Huffman encoding process. Okay, now when we transmit the information, whenever x1 is there, we would transmit 1. Whenever x3, for example, appears in your sequence, 0, 1, 0 would be transmitted, and the decoder knows how to get back the original information. Okay, very simple and very effective step. Okay, again, to repeat, you got to sort them in descending order of probabilities, descending order of probabilities. Then combine the second step. The second step is to combine the two lowest probabilities, Then again, you go back to step one, until the combined probability is 1. Okay, until the combined probability equal to 1. Then once it's done, then you just encode the branches with zeros and 1, encode the branches. So it's very simple process, and even you can implement this in an algorithmic way very efficiently or very simply. So that's why this technique is still popular. It's pretty much used in all lossless compression schemes that one encounters. Now, the next steps of this process is that how efficient this particular coding scheme was. If you remember before that, we picked up the formula for efficiency was nothing but, we know from Shannon's theorem, nothing can go below the entropy. So the efficiency is given by the entropy divided by L average. And let's compute the entropy of this given problem. The entropy of the given problem, h of x, we have 4 symbols, k going from 1 to 4, and we know the probabilities of each one of them. So we take those probabilities and we weight them, and that's the entropy formula. The entropy of this particular example turns out to be 1.73 bits per symbol. In other words, whatever compression we do, we cannot go below 1.73 bits per symbol. Okay, so let's pause for a while and let's assume we didn't know the concept of entropy. And if you were given these 4 symbols x1 to x4, and if I have asked you to code them, you would have gone with definitely with 2 bits per symbol, because we have 4 levels, and from the knowledge we have before, from using the fixed length coding, we know 2 to the power of 2. We need 2 bits for each of them. So you would have went with the coding scheme. Maybe for x1 you would have used to 0 0, x2 you would have used to 0 1 1 0 1 1, for example. Okay, and in this approach, in the fixed one, this also is some form of a prefix-free code. But what has happened is that this is not an efficient scheme, because on an average for each symbol, I'm using 2 bits. Okay, here I'm using 2 bits per symbol. That's not optimal. Okay, and we use 2 bits per symbol, whereas the entropy says you can go up to 1.73 bits per symbol. This matters a lot when we deal with data which is megabytes and gigabytes and terabytes of information. This level of reaching to the entropy is so important there. Okay, so 2 bits per symbol is what we would have known if we didn't know about encoding entropy and Huffman. But by knowing a Huffman thing, now we need to find out what is the efficiency now. Okay, so previously, if we didn't know this thing, the efficiency with the fixed length coding would be 1.73 divided by 2, whatever it turns out to be. I think it's around approximately around around 87%, approximately 87%, 1.73 divided by 2, 87%. Okay, so 87% would have been an efficiency with the fixed length coding. But now with the Huffman one, we can determine L, which is average code word length, L, this should be L, the average code word length, L. So that's nothing but taking the number of bits. So x1 here we have 1 bit, and the associated probability is 0.4. X2 is the length of 2 bits, the associated probability 0.35, and likewise. And when we work out, it shows out by using Huffman coding, because each symbol is having different probability, and we know from the coding that higher probable symbols will be given lower bits. By using that concept, we are getting at 1.85 bits per symbol. Okay, now in terms of the efficiency, this should be efficiency formula. Efficiency is given by hx by L. It's 1.73, which is entropy divided by the average length, which is 1.85, it 93.5. Okay, so there you go. So by using the idea of the probability and using the Huffman coding, we have improved the efficiency, which was before by using fixed bits, which was around 87%, to almost 94%, a 7% improvement just for this very simple example by using variable allocation of bit length. Okay, so that's a key advantage of the Huffman coding, and this example pretty much covers many of the concepts we have seen. So the thing to remember in any coding is to compute what's called coding efficiency. It's nothing but entropy divided by the average code word length. And by doing this one, we can determine the efficiency. Now, there is still room for improving the efficiency from 93.5 to 100%. Can we reach the level of h of x is the key question. Yes, you could reach it if we use maybe other variations, not really Huffman coding, or other extensions or modifications of Huffman coding. So there are many other lossless schemes, and that's where you could apply your creativity in bringing the efficiency even more closer to 100% or closer to entropy. And we cannot definitely go below 1.73 bits. If we do it, it means it's not anymore lossless. You might be entering the lossy territory. So continuing on with this example, because we are now taking examples, continuing with the example, let's take another example to further validate what we are seeing and see whether we could do some simple modifications to improve the efficiency. Okay. So the second example I'm giving you is with two symbols. Okay, let's take two symbols. The probability of getting x1 is 0.7, and the probability of getting x2 is 0.3. Okay, now if you were to work out the entropy of this one, the h of x, the entropy of this one is nothing but 0.881 bits per symbol. Okay, so the idea is that by using this probability information, when you plug into the entropy expression h of x, which is nothing but pk log pk, and you add them all, and when we do this, you find out that the overall thing, it says the entropy is 0.881 bits per symbol. So whatever you do to this, you can only compress to the level of 0.881 bits per symbol. But let's say if we didn't proceed with any of the scheme, now it's easy to code this one. Okay, obviously x1, I would code it as, for example, 0. Okay, and x2 I would have coded it as 1. Okay, so I would have given 1 bit for each of the symbol. So the average code word length, L average, or L, the average code word length is 1 here. Okay, because I'm using 1 bits per symbol, and when you do the average of 1 times 0.7 plus 1 times 0.3, it's 1 again. Okay, so the efficiency of this coding scheme is nothing but 0.881 divided by 1. It happens to be 88.1%. Very simple example, 88.1% is the efficiency we are getting with Huffman coding. In this case, the Huffman coding is a simple two-symbol example, and the coding is similar to the fixed length coding because it's two symbol. Now, what I'm coming at is that we could always do, because whenever we send information or whenever we store information, they tend to occur in series. I mean, the information flows as we go by. So it might be possible that the particular source is generating something like x1, x1, x1 like that, or x1, x2, x1 like that. Those are the possibilities, no other way, okay, because it's all transmitted in binary form. All that you get transmitted is ones and zeros here. So why don't we, instead of encoding one symbol at a time, x1, x2 separately, why don't we encode two symbols? And that's called the second order extension. Essentially here we are trying to encode two symbols at a time rather than one symbol. If that's the case, now I'm defining 4 new symbols, A1, A2, A3, A4. And what is A1? A1 is nothing but x1 multiplied by x1. It's possible that x1 and x1 would appear next to each other when it's stored or transmitted, something like 0, 0 with the given previous example. So I'm having a new symbol A1, which is x1, x1. A2 is x1, x2. A3 is x2, x1. And A4 is x2, x2. Now I have to revise the probabilities. x1, x1 is nothing but probability of x1 times probability x1. It happens to be 0.7 times 0.7, which is 0.49. So that's your first probability. x1, x2, again, the probability is 0.7 times 0.3, it's 0.21. Similarly, probability of x2 and x1 is 0.21. And finally, when you have x2, probability of x2 times x2 is 0.09. Okay, when you add all of them together, it will add to 1. That's for sure. So here we have just considered instead of just coding x1 and x2 separately, we are going to code them combinedly. It's called second order extension. When we now do the Huffman tree on this one, Huffman tree, we sort the probabilities in descending order, and we have done this thing. The probability sorted in descending order, 0.49, 0.21, 0.21, 0.09. We have done that. Now, going through the next step of the Huffman process, we would combine the two least probable events. So here is two least are these two, and we get the new probability to be 0.3. Then we would sort them again. So we would sort 0.49, 0.2, and 0.3. And 0.3 is greater than 0.21. So that would be moved before 0.21. So that's what happens in the next step. Again, it's in descending order. The descending order would be 0.49, 0.3, and 0.21. Now, in this thing, we will combine the two least probable events. The two least probable events are again 0.3 and 0.21. So 0.3 and 0.21 would be combined to give the new probability 0.51. Now what's left is 0.49 and 0.51. Again, we would do the descending order. So 0.51 goes greater than 0.49, and 0.49 goes to the lower branch, and there you go. So that's again 3-step process to get the Huffman tree going, and finally we will end up in getting 1. Okay, that's the final step. When we reach 1, it means the Huffman process has ended. Now when we start to code the branches of the thing, again we use the 0, 1, 0, 1, 0, 1 to code it. Okay, so now it's just has become very simple now by just tracing back the code word of, for example, here A1, the code word of A1 branch is only related to this particular aspect. So this is so code word of this one is 1, whereas A2 is related to this branch. A2 is this branch, and it comes directly here. So it's 0, 1. Okay, you have to read it backwards, as I said. Similarly, for I will use a different color. The branch for A3, the branch that represents A3 is obviously this 0, and then it goes through here, and it comes and it goes. Okay, so it's 0, 0, 0. Likewise, the branch for A4 would be 0, 0, 1. Okay, so if you see, this is an Huffman code. Again, it's prefix free. None of the code word is a prefix of another code. So it's instantaneously and uniquely decodable. Now let's just go one step further and see what has happened to the whole formula of the efficiency here. Okay, so again, we will compute the entropy of the A's. The entropy of the second order extension is 1.762 bits for 2 symbols, because we are encoding 2 symbols at a time. So it's 1.762 bits per 2 symbol. In other words, if you take this entropy per symbol, the entropy hasn't changed. It's the same as what we have seen with the first order case. Okay, the entropy pretty much is same. But here with the second order extension, we are just keep in mind it's 1.762 bits per symbol. Now, if you work out the L average of this particular example, L average of this case using the probability L average, it happens to be the L average is the bit size 1. It would be like 1 times the probability 0.49 plus 2 bits for the second one times 0.21 plus 3 bits for the next one. Again, the probability is 0.21 plus 3 bits and the probability is 0.09, and we add them, it's 1.81. Okay, so that's average code word length for the second order extension. Now, when you compute the efficiency of this new coding scheme with the second order extension, again, entropy divided by the average code word length, so 1.762 divided by 1.81, the coding efficiency here is 97.3%. Okay, so the same thing which we had before. Okay, previously we had just the first order and we coded that as 0, 1. The coding efficiency there was 88.1. We haven't done anything. We, instead of coding 1 symbol at a time, we are coding 2 symbols at a time, which is easily doable because typically these samples are transmitted in continuous way and they're in a series. So instead of encoding 1 at a time, we are encoding 2 at a time. When we do, it's called second order extension. During the second order extension process, we have found that the efficiency, which was 88.1 before, has moved to 97.3%. Massive improvement in the coding efficiency. So this gives an idea that even with the Huffman code, just by doing an extension in the order, you can get an efficiency which is almost 100%. Now, you might be wondering, can we keep continuing on? Yes, nothing stops you by going to a third order extension, fourth order extension, and so forth. Eventually, you might reach the level which is closer to the entropy level. In other words, we will reach this bound 1.762 with higher order extensions, but at a certain point, it may not beat that 1.762 because that's what the theorem says. So we are governed by the information theory of entropy. In other words, nothing below entropy. So that's why it's so important for us to know what would be the entropy of a given source. And entropy is a very simple formula just based on the probability distribution. So if you know your source probability, you can compute the entropy, and that gives an absolute lower bound that one could reach. Now you can design prefix-free codes by using the simple tree structure of Huffman process, arrange the symbols in descending order of probability, combine the least two probable events, and again go through the descending process, and you continue this step until you reach one. Then you just start to encode the branches of that Huffman tree to 0 and 1 and start to read the code words in a backward direction. That's it. Now, by chance, if you flip the encoding process, instead of 0, 1, you make the coding process like 1, 0, 1, 0 for the branches. Nothing changes. Just the 1 has become 0, 0, 1 has become 1, 0, 1, 1, 1, 1, 1, 0. Again, it's a prefix-free code. So as long as one code word is not a prefix of another code word, flipping 1 and 0 in a consistent way is not going to impact. Okay, so just to keep in mind. So that's essentially an idea on how we can proceed in saving the memory requirements and the bandwidth requirements of a digital biomedical signal. Okay, so towards this end of this topic, it's many ways that we could work on in essentially achieving a compact representation of a digital biomedical signal. Either we could change the sampling frequency, because in many cases we understand a signal would have been oversampled above the Nyquist rate, so you can adjust the sampling frequency to reduce the number of samples we need, enough number of samples in an optimal way. Second way is that when you do the quantization process, you can adjust the quantization process in a way that the quantization noise is not really bothering you. That's the second aspect of reducing the number of bits. The third one is going through a formal aspect of something like an Huffman coding that we just discussed to provide a lossless means of doing it. Now, you can also go one further steps of just storing the features alone, like the AR model coefficients and things like that. It is somewhat lossy, but that loss is manageable. It's acceptable because the loss is not really taking away the distinct features of your signal. So rather than storing the entire signal, we could just store the AR coefficients or other model parameters. Basically, the features here are also playing the role of compression. Okay, so it's happening hand in hand. So that's why this particular aspect of linear prediction, which is basically an AR coefficient, a linear prediction followed by compression is also called linear prediction coding. And you do have various schemes where LPC or linear predictive coding has been successful in covering both it as a feature analysis technique as well as a compression technique. So there are many other variations, as I indicated, for other lossless schemes. The only importance that you need to remember is that with the Huffman coding, yes, we know we can improve the efficiency by increasing the order, in other words, encoding multiple symbols at a time. But it might add to the delay or latency in the system because we have to encode more than one at a time. In some cases, it might be a little bit time consuming, but it again depends on the context and the application. You need to keep in mind. Okay, so with that, it brings a nice summary to what we have discussed, right from sampling, to quantization, to fixed filtering, to adaptive filtering, to feature extraction, followed by compression either for storage or transmission. So this particular pipeline that we just covered fits into the classical biomedical signal processing applications, and also with the emerging applications in telemedicine and telehealth, where patients could stay at home, long-term care facilities, or in remote locations, and their vital physiological signals could be monitored in a way that we take care of efficiency from the bandwidth and also from storage. When we do this thing, indirectly, we are also uh, helping the power requirements. In other words, the battery could last longer when we work with fewer samples compared to more samples. So that's a key aspect, which is a software solution in making sure that your devices don't run out of battery power. So that's where it becomes important from an engineering point that we also take care of the low power requirements needed essentially in a lot of wearable and Internet of Things type health applications that are emerging, where we need the batteries to last as much longer as possible, so that we could track people having chronic health conditions in long-term cares and also in other elderly care facilities. Thank you.